Now this expression, big G, big M, little m over r, it had a negative sign in front of it. It was the work required to move this small mass m from distance big R from the large mass to infinity against the gravitational force. Gravitational force is conservative. I've asserted that, I haven't proven that, and I might not actually prove that in this course, although it's going to be very easy to prove. Then this expression, and where I don't have the negative sign, that's the change in potential energy from distance big R to infinity. So clearly your potential energy is increasing because you're pushing against a gravitational force. If you stop pushing, the satellite could fall back and gain kinetic energy. The other thing that's really kind of interesting is, okay, I can write up here, this is our first now at distance little r. I used big R here so we could distinguish the variable of integration from the limit on the integral, but I can rewrite the thing in terms of little r. Potential energy, and this board is really precarious here. You can root for a collapse if you like. Potential energy at distance r is this. The kinetic energy at distance r, we calculate it to be this. So that's potential and kinetic energy at distance r, and we note that the potential energy is positive, the kinetic energy is, potential energy, wait a minute, okay, sorry, the potential energy should be negative, and I'll explain that in a minute. I had a brain lapse there. Potential energy is negative, big G, big M, little m over r. The kinetic energy is 1/2 of the magnitude of that potential energy. Kinetic energy is 1/2 the magnitude of the potential energy. That's a very interesting and profound result that we're going to explore and utilize here shortly, more or less immediately. Okay, so where are we? Going from r to infinity, and from any point, well, going from r to infinity, at least along a radial line, a line starting at the center of the planet, going through the position of the satellite and continuing on to infinity, we have the work done by the gravitational force on the object is negative big G, big M, little m over r. So the change in potential energy is equal and opposite to this. It's plus big G, big M, little m over r. Now, I got a little backwards in one of my comments, or one of the things I said before. I corrected it at the time, but let's see where the correction needs to be, and let's make sure we understand how this works out. The potential energy at infinity is clearly greater than the potential energy at r, because you've got to do positive work to get from here to infinity. Gravity does negative work going from here to infinity. Either way, we have greater potential energy at infinity than we have at r. Now, the potential energy at r then equals the potential energy at infinity minus the change in potential energy from r to infinity. Think about that until you're convinced you understand it. So that if the potential energy at infinity is taken to be 0, which is the convention, so put a big old circle around that. Didn't mention it before, but we're busy doing the integral and so forth. The potential energy, if we take the potential energy at infinity to be 0, and for reasons I'll discuss in a minute, that's the only reasonable choice of where the potential energy should be 0. Then it follows that the potential energy at distance r is potential energy at infinity, which is 0, minus the change in potential energy, which is plus G big M little m over r, so it'll be minus that, and that's going to be negative big G big M little m over r. The result is that at any point we have a negative potential energy. Now, there's no other really good point that we can universally use as a point of reference for the potential energy. We could use the surface of the Earth, and then we'd have a different potential energy function, but it would just be this, and then we'd add a constant, which is equal and opposite to the potential energy at the surface of the Earth. We could do that. We could complicate things by integrating from our Earth to infinity, or from our Earth to distance r to get the PE of r, and we'd have a different function, but it would just be this function with an added constant. The way we understand this is our potential energy at distance r is equal and opposite to the work we got to do from here to infinity to move an object from this point to that point. Actually, I'm not going to elaborate on that right now. Let's just accept that, because I really kind of need a diagram. Don't have a place to put it, and we'll do that in the next clip. Okay, so we accept this, and we'll see the implications of this very shortly. This means that with this convention, very conveniently, well, we've already figured out that the kinetic energy of an orbit, a circular orbit at distance r, is this. How does this compare to this? Well, it's just half of this if you ignore the negative sign. So the kinetic energy has half the magnitude of the potential energy. And if we want to get the total energy at distance r, it's just the potential plus the kinetic, the negative here, plus something that's got 1/2 its magnitude but is positive, and we just get 1/2 big G big M little m over r. So there's your total energy function for an object in a circular orbit at distance r. And these three quantities have an obvious relationship. Kind of easy to remember them, especially if you don't put that little smudge on and get a square in the r when you write this quantity. I think I started to do that right here. Again, you got to be careful. Okay, now, force of gravity is conservative. How do we establish that? Well, on the radial line, that is the line of which we integrated, what does it mean for force to be conservative? It means it's the derivative of some potential function. Well, here's our potential energy function. We take the derivative of that potential energy function. What do we get? Well, derivative of this is, the derivative of 1 over r is negative 1 over r squared. This is going to give us big G, big M, little m over r squared. What's that? Well, that's our gravitational force. So we've shown that the gravitational force is the derivative of this function. So gravitational force, we'll put a graph on there, is the derivative of this potential function. Now I put quotes around this because there is a gravitational potential function that's not equal to this potential function. It's equal to this potential function if you take the mass little m out of it. We'll talk about that later. Okay, now in space, remember, if this force is conservative, it doesn't matter how we get from position r to infinity. We don't have to go directly away from the planet. We could spiral out. We could follow any old path we like, and the change of potential energy should be the same. That's going to be true if the force function is the gradient of our vector function. Now, if you don't know about gradients, don't worry about this. Take this as a plausibility argument, but this can be put onto rigorous footing. And if you're taking vector calculus, you should do this. This is an exercise to help you understand vector calculus better, but also as an exercise in applying these concepts to physics, because you're going to do more of that. It's in your future. You might as well lay some groundwork now because it's not that difficult. Okay, how do we show that this is the gradient of this? Well, we could do the gradient in spherical or cylindrical coordinates, but we can convert this to rectangular coordinates very easily and do the integral, or do the gradient. In rectangular coordinates, R is just going to be the square root of x squared plus y squared plus z squared, so R cubed is that square root to the third power, so it's the 3/2 power of x squared plus y squared plus z squared. The R vector, what's the R vector? The R vector is just xi plus yj plus zk, taking, of course, the origin as the center of the planet. Now, I'll comment that this expression for the force, we previously had the expression big G, big M, little m over r squared times r over the magnitude of r. Magnitude of r is just r, so that'll become an r cubed over here. I commented on the fact that this shows you better where this expression comes from. Here's the magnitude of the force, here's the unit vector. But if we want to do the calculation of the gradient, we're going to get something in this form. This form is going to be more convenient. So that's why I've used this form here. We get this. And we factored out the big G, big M, little m here. So there's our force in rectangular coordinates. Our potential function, big G, big M, little m over r, and our potential energy function should actually be the negative of that. All we got to do is put r into x, y, z, so square root of x squared plus y squared plus z squared, and we take the gradient of that. Gradient, well, you know how to take a gradient. Gradient is a very simple operator, and you should be used to that by now in the vector calculus. And you apply the gradient to this, and you can verify that you get this. I'm not going to do that for you. You should do that. That's often an assigned problem in a vector calculus class, but again, that depends on what problems your instructor chooses to use. So if they do use it, well, you've got a preview or you've already seen it. If not, you should do it. It'll give you more insight and lay the foundation for later work.